Okay, hello everyone. This is the second part of the demo video about the um, AI group project. And in this video, I'm going to be talking about the logic of each algorithm, which was presented in the first video. So let's move on to the first algorithm. So we got DFS, which is depth first search algorithm. So the idea of depth first search is first of all, you need to have a tree, which is um, a data structure that helps us store strings. So in this case, each string represent a word in um, our game. So this tree consists of uh, consistent words. So the set of consistent words in turn t is called st. So suppose we are at turn t. Okay. So we're gonna be guessing turn 1, 2, 3, and hopefully we will get the answer within 6 turns. So a set of words to say to is called consistent if they do not conflict with previous feedbacks. So there's no conflict. So if you have guessed some word and then they give you a feedback, say yellow, green, black, black, or something. So the set of words that do not conflict with the previous feedbacks of this type is called consistent. So in other words, they are the words that can be the answer, right? Possibly. So the idea of DFS is that you're gonna perform a depth first search. So you're gonna move, visit each node in the alphabetical order, and then you keep digging deeper until you reach the end. And when you reach the end, then this word is guaranteed to be consistent because the tree is built on consistent words only. So we return the child as the final word as the answer of the turn. So this is going to be the guess of turn T. Okay. So as soon as we reach the end, we're gonna return the guess immediately. So that's the idea of DFS, and it's naive. It's reasonably good. I believe they out of 300 and 2,309 games, it's somewhere 83% success. So it's okay, not that bad, but not good either. So moving on to the next algorithm, we have the hill climbing, knowledge base hill climbing. So similar to the DFS, we also have a tree of consistent words. So it's called ST. You can see that we use the um, notation ST here. T is for we are at turn T. Okay, so the idea of hill climbing is that we start at the root and then we keep picking each character until we reach the end. Then we will obtain a 5-character words, and we're gonna choose it. I'm gonna choose it as our guess. But the way that we traverse is that we're gonna base on a heuristic function. So the heuristic function is called h on the left right here, h of I and c. So basically, h of I and c is the count of character c at index I. So what does this mean? Let me show you. So currently we are at depth 0 here. Okay, so we initialize with depth 0, and we're gonna compute the heuristic of these nodes, and whichever has a larger heuristic. So it's kind of weird because usually we move to the lower heuristic, but um, for this definition, we're going to pick the node with larger heuristic. So the heuristic of this node is going to be the count of char A at index 0 across all words in the tree. So let's count how many words satisfy this condition. So we have over here apple, apply, and this word. Okay, so 3 words whose starting with A and is consistent. It's consistent because it appears in this tria. This is the set of all consistent words up to turn T. So basically the heuristic here is equal to 3. Okay, and for this node B, we can see that there's only one. So we're going to find h of B0. So the count of character B at index 0. So there's only one word, which is black here. So it's equal to 1. And since 3 is the larger value, we're going to move to, we're going to pick this node. And we're going to add it to our, we're going to add it into our, guess word. Right? So A. And we just keep repeating the process. So for the node being A, it has only one child, so we're going to move to P as well. And then we're going to evaluate the heuristic values of P at depth 2 and then R at depth 2 because they are the children of P. And we can see that there are 1 apple and apply here, so 2 of them, which means there are 2 words whose the character P appears at the second position if we're using 0 index. For R, there's only one word, so the heuristic is 1. So we're going to pick P. So we append P to our guess word. And we keep doing that until we reach the final character, which is the last one. We have 5 characters, so it's going to be the 4th one. We're using 0 index. And if we have a tie heuristic, then we're going to prioritize the alphabetical order. So we're going to guess apple. So for hill climbing, the accuracy is better. It's actually better than DFS. I don't remember how many, but like 93% or 90% or something. You can check it in the report, and it's not the speed is like equivalent, but the frequency heuristic really helps out. In terms of accuracy. All right, so let's move to the third algorithm, which is the entropy solver. All right, so the entropy solver is our most optimal solver, and it's based on the concept of entropy. So what does this thing do? So basically, when you're trying to guess a word, suppose that you guess a word apple at some turn t. So there's going to be, we don't know what the secret word is, right? So it depends on the secret word that you're going to have different cases of, the feedbacks. So these are the feedbacks. So I draw them in yellow and green. So representing, how Wordle games is. So green means that the character is correct in position. Yellow means it's there, but it's not in that position. So we have a bunch of feedbacks, and this is the distribution. So suppose that when you guess apple and you get this distribution, you're gonna know about this distribution actually. So it can, there's certain words. There are certain words that are gonna give this feedback if the guess word is apple. There are certain words that's gonna give this feedback when you guess the word apple, and so on. So these are the potential secret words that we don't know, but we do know about the distribution of them. So given that we guessed the word apple. So this distribution, we call it FG. So F is for feedback. So because this is the distribution of feedback, so we have a bunch of feedbacks, and um, we have the frequency, the amount of words that use this feedback. So if you guess if one of these words is a secret word, then this is going to be the feedback. All right. So we're going to compute the entropy of this distribution. So it's based on the formula for entropy, which is the expected value of logarithm of base 2 of the probability. So why do we compute this value? If you are familiar with information theory, entropy represents the uncertainty of a distribution. So the more entropy, the higher the value of the entropy, the more information gain we're gonna have after guessing a word. And this is actually proven in the context of the report, so you can check it out. But intuitively, you can say that if the entropy is large, then we are expected to prune more words from the set of consistent words. So in other words, you may have a bunch of words that can be the candidate, and after you guess a word with a large entropy, a large expected entropy, it's going to prune down a lot of these words, and the remaining possible answer is expected to be small. So maybe you can think as like this. So if a distribution is uniform like this, then the entropy H is large, right? So if all of these have the same chance, then the frequency is gonna be like the distribution. The frequency is gonna be small because they all have the same word counts. Whereas if you have a non-uniform, it may look like this. So um, you may have small pillars, and you may also have like really the feedback to have a lot of words corresponding secret words. But if you have a large entropy, maybe it looks something like a uniform distribution. So if the amount of words here is small comparing to this large thing, then it means that if you if we receive one of these feedbacks, then the amount of possible answer is only this much, right? Say that I received this feedback, then this the height of this thing is how many words left that can be the answer. So there it is pretty small comparing to when you get a feedback somewhere here, and then this is the distribution. So you have many words left that can be the answer. So you may prune down more words if the entropy is large, and when the entropy is small, the amount of words left is really big. It can be big, and you prune down like not many of them. So it's a little hard to explain this in an intuitive way, but I did really try my best. So maybe you can read the report for more intuition as well as for more proving. Okay, so let's move on to the last algorithm. Oh, and by the way, the entropy algorithm, it works 100% success on all 2,309 words. So it is a very good test result. It's the best that we have. Okay, so let's talk about the final one, which is the progressive entropy sampling. So the idea of this algorithm, it also uses entropy, but um, actually the entropy algorithm of here is very costly. Okay, so the entropy is very costly. So we're trying to reduce the computation. Okay, so we reduce the computation by what method? So we're gonna just do a sampling. We're not gonna compute the entropy of every single um, distribution, but we're just gonna take a few words out to compute. So we're going to have a parameter S here. So S represent the number of the samples per node. So you can see it on the pseudocode over here. So for the context, we are also working on a tree of the, oh, this tree is different from the first two algorithms. So DA is the set of all words. So which is like 13,000 of them. So this tree is fixed. It's not updated after each iteration, after each turn, but it's going to be fixed. So that's the difference. Okay, so back to the point. So the idea to reduce the computation is that we're going to use a Monte Carlo sampling. So what does this mean? So not usually, but in the context of the full entropy, which is the previous algorithm, you're going to compute the entropy of every word, right? And then you pick the largest entropy. This is the previous algorithm. But now we're not going to do that, but rather we're just going to sample some words and then we compute their entropy. So first we're going to at the root node, we're going to consider two children, A and B. And then we're going to do a Monte Carlo sampling on the node A. So we're going to sample S words. So this is a parameter. We're going to sample that amount of words. So we're going to do a Monte Carlo traversal down here. Pick randomly two words. Okay, suppose that we pick apple and apret here. So after picking our sample, we're going to compute the entropy of these two words only. And then we're going to add them up and divide by the number of the sample size. So in other words, we're computing the average entropy. And we use that as our heuristic for that node, for node A. Okay. So after we obtain that heuristic, and then we obtain heuristic of B, we're gonna compare which one of them is larger. If heuristic of A is larger, then you're gonna repeat the process with A. So you're gonna consider all children of A, which is P, or maybe something else over here, and you repeat the process. And eventually you're gonna reach a final prefix, right? And you're gonna also cache all the words that you have computed entropy. Okay, so I'm gonna add this word into the cache, this word into the cache. So all of these, I have a bunch of words that have computed entropy of, right? So it's not the size of this this set is not big as the original 13,000 words, but it's big enough so that you're gonna get a good large entropy out of it, large entropy word out of it. So you're gonna use this word as the guess. Okay, so in summary, for progressive entropy, you're not gonna compute every single entropy of every single word, similar to how the previous algorithm does, and obtain the largest one. But you're just gonna create a sample that is good enough that you can get a word out of it. So the sample is built based on traversal using heuristic and Monte Carlo sampling. And again, for more information, maybe you can read the report. And I think that's it for this demo. Thank you for watching.